Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating paper, DeepRAG, Thinking to Retrieval Step by Step for Large Language Models. I came across it in ArcSieve.
Oh, DeepRAG. I saw that one pop up too. Sounds like another attempt to tackle the hallucination problem in LMs, right? The eternal quest for factual grounding.
Hallucinations, my favorite topic, or rather my least favorite considering how pervasive they are. Retrieval-augmented generation, RAG, is supposed to fix it. So, what's different about this RAG?
RAG in general seems like a band-aid solution, doesn't it? Just throw more data at the problem without really understanding how the model reasons about that data. But I am interested to hear what the paper is about.
Well, the core idea is that instead of just blindly retrieving information all the time, DeepRAG models retrieval as a Markov decision process, an MDP. Basically, the model strategically decides, at each step of generating an answer, whether to retrieve external knowledge or rely on its internal parametric knowledge.
Okay, interesting. So it's trying to be more selective about retrieval. That makes sense. RAG can often introduce a lot of noise if it just pulls in everything remotely relevant, right?
Exactly. It's like giving someone all the ingredients in the kitchen and expecting them to make a gourmet meal. You still need to know how to use those ingredients. The model needs to know when external knowledge is actually needed and when it already has the answer or can reason it out itself, and not be fooled by plausible sounding but wrong information.
So, it's a decision-making process at each step. That sounds computationally expensive, but I suppose if it improves accuracy and efficiency, the trade-off might be worth it. What kind of task decomposition are they doing?
That's a great question. According to the paper, DeepRAG iteratively decomposes queries. So, instead of just throwing the whole question at the retrieval system at once, it breaks it down into smaller, more manageable subqueries. And at each step, it decides whether it needs more information or can proceed with what it already knows.
Like breaking down a complex problem into smaller, solvable parts. That's a common strategy in AI, but applying it to retrieval is pretty neat. It also makes the retrieval more targeted and specific, reducing the chances of pulling in irrelevant information.
So it's like asking clarifying questions before trying to answer the main question. Instead of regurgitating everything it finds, it's trying to understand the context better.
But how does it decide? What's the criteria for determining when to retrieve and when to rely on internal knowledge? Is it based on some confidence score or some measure of uncertainty?
That's where the MDP comes in. They define a reward function that encourages accuracy and efficiency. So, the model learns to take actions, either retrieving or generating, that maximize this reward. I think they used a combination of metrics like answer correctness and retrieval cost in the reward function.
Okay, that makes sense. Reinforcement learning to optimize the retrieval process. Smart. So, the model basically learns to think about whether it needs to consult external sources at each step. I like that. It mimics, to a small degree, the kind of metacognition we use when tackling complex problems. Like, do I know this? If not, where can I find the answer?
But is it really thinking, or is it just learning statistical associations between query patterns and retrieval actions? That's my perpetual skepticism rearing its head. Is there any actual reasoning going on, or just pattern matching on a grand scale?
I'm with Sarah on this. It sounds like a clever optimization technique, but I'm not convinced it's addressing the fundamental issue, the lack of true understanding. It's still operating within the confines of the existing deep learning paradigm, which, in my view, is ultimately limited by its inability to handle spatiotemporal relationships effectively. What did the paper say about improvements to answer accuracy?
They reported a 21.99% improvement in answer accuracy compared to baseline RAG methods, which is pretty significant. They also found that it improved retrieval efficiency, meaning it retrieved fewer documents overall.
Wow, almost 22%. That's a pretty substantial jump. If those numbers hold up under scrutiny, that's a real win for the RAG approach, and a step closer to more reliable LLMs. Makes me wonder what data sets they tested this on. What are the limits? What happens when you get a very novel question that's never been seen before?
That's the crucial question, isn't it? Cherry-picked datasets can be very misleading. I'd want to see how it performs on genuinely challenging, ambiguous, real-world queries that require nuanced reasoning and the ability to synthesize information from multiple sources, including sources it wasn't explicitly trained on.
And how well does it generalize to different domains? A model that performs well on question answering about, say, historical events might completely fall apart when asked about scientific concepts or abstract mathematical principles, because the representation of information and the relationships between concepts vary wildly. Are they just testing it on simple fact recall?
They didn't specify the different coordinate representations in the paper. I can speculate this approach might struggle when you have to integrate across different domains or sources that use very different terminology or conceptual frameworks. That might require a more sophisticated understanding of context and semantics than this model currently possesses.
That sounds like AGI territory. Is there any mention of limitations in the paper? I suspect if this was a magic bullet for all the hallucination problems, it would be all over the news. But no results are perfect, you know?
And even if the accuracy is high, what about explainability? Can we understand why the model made a particular retrieval decision? Is it just a black box spitting out answers, or can we actually trace the reasoning steps? If it's the former, it's just another incremental improvement in performance without addressing the fundamental problem of understanding.
Exactly. It's like a student who gets all the right answers on a test but can't explain how they arrived at those answers. It might be impressive on the surface, but it doesn't demonstrate true understanding. What happens when the model encounters conflicting information? Does it have a mechanism for resolving those conflicts, or does it just blindly regurgitate whatever it finds first?
The paper doesn't go into great detail about those limitations, but from my perspective, one of the biggest challenges is still mapping between different symbolic representations. The model is essentially translating natural language queries into retrieval queries, and then translating retrieved documents back into natural language answers. But it might not be able to handle visual images or other modalities as seamlessly. The human brain is much better at seamlessly switching between different sensory modalities and representing them in a unified framework.
That's a really interesting point. We can easily take information from a diagram and immediately discuss it. LLMs would have to struggle with the image, get some object recognition system involved, translate that, then cross-reference. The list goes on. It's not a unified understanding like our own.
Which highlights the need for more robust neuro-symbolic architectures. We need systems that can combine the pattern matching capabilities of neural networks with the symbolic reasoning abilities of traditional AI. That way, we can build models that not only perform well but also provide explainable and reliable answers, even when dealing with ambiguous or conflicting information.
And that neuro-symbolic architecture needs to be able to handle different coordinate systems effectively. The way we represent spatial and temporal information in the brain is incredibly complex and flexible. We can seamlessly switch between different reference frames and integrate information from different sensory modalities. Current AI systems are nowhere near that level of sophistication.
I agree. I think research into how the brain encodes spatiotemporal information, particularly the role of neural oscillations and synchrony in representing sequences and events, could offer crucial insights into designing more effective AI algorithms for reasoning about time-dependent relationships. Maybe we can create something that handles long-term memory and context in a more biologically plausible way.
Yeah, that's a crucial area for exploration. We don't even fully understand how the human brain does it. We think our memories are stored in the hippocampus, but then how is that connected to the neocortex for long-term storage? There are definitely a few mysteries to unlock before we can build truly intelligent machines.
And speaking of the hippocampus, what about integrating the principles of hierarchical temporal memory into AI frameworks? That could be a way to better handle long-term memory and context, which is something that current LLMs struggle with. That may be the path to more robust systems.
But hierarchical temporal memory, like many neural network-based approaches, might still be limited by its representational capacity. It might be good at recognizing patterns and sequences, but it might not be as good at abstract reasoning or generalizing to novel situations. It might need to be combined with some form of symbolic reasoning to truly reach AGI.
That's a fair point. It's not just about mimicking the structure of the brain, but also about understanding the underlying computational principles. And that might require a hybrid approach that combines the strengths of both neural networks and symbolic AI. It's like, how do we map between visual images and the underlying symbolic representations?
That may be the key, but at the end of the day, is it just all about more compute power? We keep scaling these models up and they keep getting better. But I'm not sure that's the path to AGI, as we've discussed. You need a theoretical framework to guide that brute force approach. Otherwise, you are just lost in space.
Exactly. More data and more compute power can only take you so far. At some point, you need a fundamental breakthrough in understanding how intelligence actually works, and that might require abandoning the current deep learning paradigm altogether. It's not that neural networks are useless, but they're just one piece of the puzzle. A big piece, but only one piece.
I suspect we need to get away from the brute force approach altogether. It is really about understanding how the brain represents and manipulates information, particularly spatial and temporal information. We need a core algorithm that can seamlessly translate between different coordinate systems and integrate information from different sensory modalities, something that transcends the limitations of current deep learning architectures.
But if LMs are thinking too fast to explore effectively, what are the specific neural mechanisms underlying human exploration? Understanding the balance between speed and deliberation in the human brain could provide clues for developing AI systems capable of strategic exploration, rather than simply rapid, brute force calculation. Maybe speed isn't the be-all end-all here.
That raises an important question. If the current emphasis on speed is counterproductive to achieving the complexity of AGI, we need to reevaluate our assumptions about the best paths to achieving such a goal. We need new metrics of measuring intelligence.
Yes, exactly. It's likely an artifact of a missing or incomplete model of the problem, not a sign of real understanding. What specific cognitive processes, if imitated, could lead to more careful exploration and deeper knowledge acquisition? Perhaps more strategic models could be explored.
Well, let's bring it all together and then wrap up. I'm interested to hear what future research directions each of you sees coming out of this DeepRAG paper and our discussion.
From my perspective, I'd love to see more research on integrating the principles of hierarchical temporal memory into AI frameworks to better handle long-term memory and context. Also, further investigation into how the brain encodes spatiotemporal information and how we can apply those insights to AI algorithms. We need AI that's more than just brute force. It's got to be elegant.
I think we need more fundamental research into the nature of intelligence itself. The focus on more and more data and deep learning feels like we're missing a crucial piece of the puzzle. We need to take a step back and ask, what is intelligence really? In the context of the universe, is it just pattern recognition, or is it something more?
I'm all about exploring hybrid architectures that combine neural networks with symbolic representations. We need to bridge the gap between statistical learning and explicit reasoning. And we need to prioritize building systems capable of genuine reasoning over merely mimicking superficial patterns in data. It needs more than just speed. It needs explainability and trustworthiness.
For me, it all comes down to spatiotemporal reasoning. I think AGI hinges on developing a core algorithm capable of seamlessly translating between different coordinate systems and integrating information from different sensory modalities. We need to move beyond the limitations of current deep learning architectures and develop new ways of representing and manipulating space and time. The world is more dynamic than deep learning allows for right now.
Great points, everyone. It seems like we all agree that while DeepRAG is a step in the right direction, there's still a long way to go before we achieve true artificial general intelligence. And it's going to require a multidisciplinary approach that combines insights from neuroscience, computer science, and mathematics.
Absolutely. The quest for AGI is one of the most ambitious and challenging endeavors of our time. It's going to require a lot of hard work, creativity, and collaboration.
And a healthy dose of skepticism, too. We need to be careful not to get caught up in the hype and to always question our assumptions. Because the path to true intelligence is likely to be more winding and unpredictable than we currently imagine.
Exactly. And we need to be willing to abandon our preconceived notions and explore new and unconventional ideas. Because the key to unlocking AGI might be hiding in plain sight, waiting to be discovered.
Well said, everyone. That's all the time we have for today. Thanks for joining us on Cognitive Spirals, and we'll see you next time.